Hello there, my name is Tom Manners, and over the course of the next 60 minutes, I'm hoping I'm going to be able to take you through what mastery means when we're talking about mathematics. Now, that means different things to different people, and I'll go through some of the research behind that. What I will introduce you to is the 5 big ideas that the NCTM provide, that teaching for mastery. And you'll notice I've done that a couple of times already. That's because I'm interested in the pupils understanding the maths that we teach, but I'm incredibly interested in how we get our teachers to be presenting that to our children. We want our pupils to understand the maths they meet, then we've got to work with the staff. And I'm hoping over the course of the next 60 minutes or so, I'll present some ideas with regards to school leadership that will help you consider that, to create the teachers that we want, that coherently work together maybe to make the best journey for your pupils from whichever year you're watching this from, whether it be primary or secondary, as a matter of fact. But let's get started straight away. My name, as I said, Tom Manners on Twitter. If you're not on Twitter with mathematics teaching, it's well worth it as mathematics. And my website has a number of maths pedagogy videos that I do encourage you to watch, and hopefully will be linked into some of the stuff we talk about today. So a little bit about me, so you know that I'm coming from a background of some knowledge, I hope. I'm a specialist leader of education, my master's, my distinction in school improvement and educational leadership at University of Birmingham. I'm incredibly passionate about math leadership and math leadership within schools as well. I'm a PGCE tutor for maths at Arthur Terry Teaching School Hub, and I work with the PGCE associate teachers there, the trainees, but we call them something different. I work for the NCTM as a teaching for mastery specialist, and it certainly changed my pedagogy, it changed my approach. And by the end of these 60 minutes, hopefully I'll tell you a little bit more about how you or your schools can get involved with the NCTM, because it absolutely inspired me, and it really did change my career direction and career beliefs and what I believe I could achieve with my pupils and what I can achieve with the staff that I work with. I'm a professional development lead for the NCTM as well, and I do some of my own work on the side of that as well. Anyway, now then, this was supposed to be a live event, but as it's a video, it's going to be different. What would you have done if I was asked to ask you in 15 seconds, if I'd have asked you to do this, draw a pentagon? What would you have done? I'm going to take a guess. I'm going to go over to the camera and I'm going to draw what I think you'd have drawn, because 9 times out of 10, if not higher than that, I tend to get these two responses. Okay, that one and that one. Why would I get those? Why would I get only those? A pentagon, I have so much potential what a pentagon could be, so many different things. But why is it when I ask teachers, never mind pupils, what I'm likely to get when I ask for a pentagon, I get given these 2 examples? Why? Is because if we just show the same items, the same idea, the same representation to the pupils over and over, they'll believe that's the narrow field of what it is. Let's look at one of the first 5 big ideas, and that is variation. Now, let's make sure we know what a pentagon is first and foremost. From the NCTM, looking up a glossary, so everyone's using the right terminology when we say what a pentagon is. You can Google it, NCTM glossary, and there it is, the dictionary, if you like, that all teachers in the school could be using. Now, occasionally some of the words are a little bit convoluted, let's put it that way, but it's certainly worth starting with, because a pentagon is a polygon with 5 sides and 5 interior angles. Now, people say to me, a pentagon is a 5-sided shape. And I say, oh, is it a 5-sided shape? Okay, so does this count? 1, 2, 3, 4, 5. Let's try and get that accurate. Is that a pentagon? 5-sided shape? Well, no, it's not, because let's go back to that definition there. A polygon. And by definition, a polygon has straight sides. So I would then go 1, 2, 3, 4, 5 and go, well, is that a polygon? And no, because a polygon actually has to be closed. Now, look at this interesting, I'll just tick that one, I'll tick that one, I'll tick that one and put a cross through that one, because I'm already showing variation. One of the 5 big ideas from the NCTM. What I'm showing here is what it is, what it's also, and what it's not. And I can do loads of pentagons. So let's just go back to our definition. A pentagon is a polygon with 5 sides. And of course, that word polygon does confuse, so you can look that up as well. A closed plane figure, it's 2D, bounded by straight lines. So that means that shows the one on my camera wasn't good enough. And so the idea of our definition straight away, when I do this live with staff, I get the same answers. It's got 5 sides. So I go back to this and say, well, is that okay? I go back to this and say, is this okay? Well, they've got 5 sides. And maybe we're not being clear enough as teachers. Maybe we're not being a standardized approach as to what we should be saying when we introduce a pentagon. Look, what if this is a pentagon? Is this so let's go back to my definition of pentagon actually. A polygon with 5 sides and 5 interior angles. Now, when we're introduced to pentagons in, say, primary school, we get shown the regular one, and then we get shown the house because it's cool and it's fun. But a pentagon could be lots of different things. So 5 straight sides, and of course those sides have got to be closed. Therefore, it's a polygon. So 1, 2, I've ripped the paper. 3, 4, 5. That is a pentagon. How often is it presented in the classroom that that is a pentagon? Yet it is. It meets every criteria of what a pentagon is. 1, 2, 3, 4, 5. 5 straight sides, which is closed. Which are closed. Never mind. I could do another one. Let's do another interesting one. So 1, 2. Does the length matter? No. The features of a pentagon are that we have straight sides and that the shape is closed. So 3, 4. Do you know what? It's going to be really similar to the one I just did a moment ago, isn't it? But that is a pentagon because it fits all the rules. I sometimes ask staff to draw me a quadratic equation, and the standard one I would tend to get is something like this. They'll put the x squared first, and they'll put the coefficient with the x term, if you like, in the middle. Then they'll put usually an integer here, and they usually write equals 0. Now, we present this same thing to our pupils over and over again. They'll believe it's always in this form. So when you show it like this instead, which is, of course, the exact same equation, pupils go, well, oh, wait a second, sir. The x squared is not first. What do I do? And that's down to the teacher using variation. What's important, what we must keep, what can't be changed, and showing off what can be changed. The order is irrelevant. In fact, you know what? If I wrote this as, let's go for 5 plus x squared equals negative 5x, which happens to be the same equation, but whoa, we haven't got an equal 0 anymore, sir. This is all about variation and how we present our ideas to pupils. So the regular ones, variation, if we use just these like I did with my pentagon a few moments ago, it leads to misconceptions. That is what a pentagon is. It has to be those simple 2 that I showed you at the start. A quadratic equation has to be the one that has an x squared first, followed by an x term, followed by probably an integer equals 0. If you use just those, it leads to misconceptions for the children. So there's probing questions, almost a little bit that I tried to model there for you. Show me one. So show me a pentagon. Show me another pentagon. Show me one that no one else will show me. In other words, what we're doing is you've got to have the important parts. They must be there, and everything else we can vary, we can change. Look at the quadratic equation just then. The highest power of x must be 2, and they can't be a power lower than 0, as a matter of fact, as well. But making sure it's not has an x squared in it. In fact, let's go back to the camera. It has an x squared in it isn't good enough, because x squared plus 5x cubed plus 7 equals 2, who cares? This tells us, no, we no longer have a quadratic. So the definitions that we use are incredibly important and, of course, lead to misconceptions as well. The central idea of teaching with variation is to highlight the essential features of a concept or idea through varying the non-essential features. And of course, as I said, it's one of the 5 big ideas. Now, pupils respond to maths very differently. Some pupils say, I hate maths. It's all rules, rules, rules to remember. Some pupils love maths. There are no rules to learn, they say. Now, in these, what seem to be identical twins, one seems to be enjoying maths because she's made connections. It makes sense to her. She understands what's going on. The girl on the right, as I'm looking on screen here, she's not particularly happy because she's not been taught that interconnection of maths. And that's what it says in the national curriculum. Maths is an interconnected series of ideas, and it's hierarchical. Understanding is remembering in disguise, as Willingham says. And when we've learned something, we can build upon it and say, well, what did we learn before? Let's now extend that knowledge to go a little bit further, as opposed to today we're adding fractions and not making any reference to any previous lessons that might just help build confidence or help build understanding. The girl on the left-hand side has been taught those connections and enjoys those connections and embraces them as well. And maths is all about making connections. It's as if I prepared this beforehand. When you're looking at GCSE here, this is the maths curriculum, and look at all those nodes there representing topics, transformations, ordering decimals, no matter what it is, 164 nodes, but look at all the lines that are being joined up to each other. And those nodes are connected by how many? 935 links, where prior learning is required to be able to access the other. So do your schemes of work make those clear? Do your teachers make those clear? Does the scheme of work say to the teacher, tell you what, before we start teaching this, are these building blocks ready beforehand, because they're going to be very important and actually going forward as well, come to think of it. For example, equivalent fractions is linked to adding fractions, because you need to be able to work out what equivalent fractions are before you can do adding fractions. Again, making those connections. The circles here represent units of knowledge. The ovals are schemas and the lines represent connections. So these new pieces of information coming in, and as you can see, the bonds are made stronger, if you like, if they're connected to previous pieces of information. As I said something similar from Willingham, understanding is remembering in disguise. Retrieval is a powerful memory modifier. Oh yes, we've seen this before, haven't we? And it makes it stronger in the long-term memory. And bringing some of those previous ideas, what I said were the hierarchical ideas that we've learned before in maths, bring them into the working memory because they've been stored, and those connections make them stronger in the long-term memory. So what is mastery? Well, people say a lot of different things about this, but the Bloom 1968 paper is kind of a big deal in this topic. Bloom believed there are 5 variables that need to be considered to create successful mastery learning. Now, I'm pleased to say that the teacher is not in charge of all 5 of them, as a matter of fact. The pupil does have some input, and so do schools and their leadership. And let's have a look at what they've got. The time required by the learner. We accept that pupils, well, the point of this, by the way, is everyone can learn maths. There's no such thing as a maths brain. There is no research to suggest that at all. However, it's believed that successful learning of maths can happen. The time required by the learner may vary. Okay, so some pupils, just to acquire some of the basic concepts, might need a bit more time. The approach taken to meet individual learners' needs. So maybe how it's represented in a slightly different way, explained in different words. And we'll look at representation as one of the 5 big ideas today. The amount of time allowed by the provider for the pupils. Yes, leadership. You look at the primary schools that provide the extra time for the maths basics. I know it's not necessarily easy to do that in secondary schools, but the amount of time allowed by the provider. I know a secondary school I worked with recently that didn't even have a maths teacher teaching maths in year 7. They've just taken away time from the pupils. The verbal ability of learners to enable them to solve problems and to reason. So coming to the teachers now. Not only the approach is taken to meet the individual learner's needs, that's down to the teacher, thinking about how can we explain something, what representation can we use to understand what's going on. The verbal ability, making pupils talk in your lessons. Teacher talk, which I'm very aware is what I'm doing right now. Verbal ability of learners, get them to talk, teacher to pupil interaction. And I'll show you a Rosenshine quote later on, that 23 minutes of a 40-minute lesson, the most successful maths teachers, 23 minutes is in conversation, discussion, ideas back and forth. I'll give you more on that in a moment. But it's not 5 minutes of the teacher and 30 minutes of solid practice, because it's probably not very good practice either. And the amount of time a learner is prepared to give towards their work. Hallelujah! The pupil does have some impact on their own journey. And that maybe just makes you feel a little bit better as a teacher sometimes, knowing that pupils do have to put it in as well. Guskey wrote this paper in 2010, The Elements of Mastery Teaching. And some of these are referred to well, I've referred to them already, I would say, over the course of this presentation. Diagnostic pre-assessment with pre-teaching, i.e., do they know some stuff already? Am I going in too low? Am I going in too high? High quality group-based initial instruction. Now, I think that's really important, because group-based means more discussion for everybody in the pupil, in the class, sorry. If you've got one group doing some work and, oh, they were doing really well, push them onto a different topic because they're doing really well. Well, can they have the same group-based initial instruction? Can they have the same group-based discussion if these pupils are still on the basics, but I'm going to make you do a different topic because you're really good pupils and you should be doing something much, much harder? Or should everybody doing the same topic, but at different depth? High quality corrective instruction, enrichment and extension activities. Now at the bottom, you'll see that, and that's very much in line with the national curriculum, where we've got fluency, reasoning and problem solving. Some would say differentiation by depth. So everyone in the pupil is still doing the same topic, so we can have that high quality group-based initial instruction, but some pupils are doing it at a different depth, but we're still talking about that same topic. This graphic here comes from Mark McCourt's book, Teaching for Mastery, from 2019, and the similar things are shared here. Testing the prerequisites, and if not everyone's on 80%, some pupils will move on to enrichment and enhancement. That does not mean a harder topic. That means more problem-solving activities, making the pupils think on a topic. And then when they can do that, brilliant, we move the class on. By the way, I'd like to make sure I'm not advocating mixed attainment classes ahead of grouped attainment here. Every class is grouped. Well, pardon me. Every group is mixed attainment, no matter how much you try to group them. What I do believe is in whole class instruction. Let's carry on. Mastery Learning's research from the EF in 2018 showed that Mastery Learning keeps learning outcomes constant, but varies the time needed for pupils. So in my example, maybe before, while the higher attainers are moving on to problem-solving activities, they're still on the same topic, which gives more time to the first group of pupils who are struggling just to get the basics of what we're trying to understand in this topic. Give them more chance to become proficient or competent at the lesson's objective. Mastery Learning breaks subject matter and learning content into units with clearly specified objectives which are pursued until they are achieved. This very much links in with Rosenshine, small steps, very much links in one of the 5 big ideas from the NCTM, coherence. Small steps are easier to take. And in fact, today is the 25th of May, the day I'm recording this. I'd have started recording this a few hours earlier, but then Ofsted released some new guidance today about maths, so I had to read that because I'm going to be bringing it into this presentation. So I had to change it last minute for you. Now, when we look at developing our maths teachers, you've got to look back on things from the Teacher Development Trust. And the content of effective professional development points out quite clearly, professional development programs must consider both subject knowledge and subject-specific pedagogy. And it's really clear in maths, the professional development focused on generic pedagogy is insufficient. And it happens all too often that we're not giving mathematicians and maths teachers time to think about what is the best way to teach something. I ran a session recently with a bunch of maths leaders, and I showed it's just solving a very simple equation, 2x plus 3 equals 7. And I showed at least 10 different models of how it could be taught. Majority of them aren't very good. But a teacher, if they wanted to, could show it whatever way they like. Is it because that was what they were taught? Is it because, oh, I think that would be best for the pupils because they're not very good, low expectations? Or is it because they don't know what research says about the best way of modeling the question? And that's something that I'm really quite passionate about. Do all teachers converse enough to talk to each other about what are the best ways of the exposition of the maths? What's the best kind of, best is a difficult word, I appreciate, but what kind of exercises make the kids think about the questions in hand, about the topic in hand, to understand the concept, as opposed to, here's 30 questions to practice, hooray, they can do it. Do it, or can they understand it? Subject-specific pedagogy, especially in maths, is incredibly, incredibly important. And there really is a need to work with maths teachers differently to other subjects. No program that focused solely on a generic pedagogy was successful in raising students' achievement in mathematics. Just looking at Rosenshine, not enough for maths. Research shows, although it certainly applies to it, research shows that leaders involved in maths CPD have the least impact, suggesting that the subject needs its own focus when it comes to teacher development. And the NCTM encouraged teachers to become engaged with maths-specific CPD. Now, mastery in maths might mean other things. Teaching for Mastery is established learning research into highly effective approaches. Piaget, Deans, Bruner, Skemp, Vygotsky, they all have brought different elements to what we now believe we call mastery. However, the essential idea and the thing I'm most passionate about is that children need a deep understanding of the maths they are learning, and that's what we should be trying to achieve as teachers after all. Of course, though, those tensions in teaching, and from this tweeter here, Chris McGrain, we've got that developing mathematicians is what we're hoping to achieve. And I know the pressure of exam results, I understand that, but that sweet spot is somewhere in the middle. And maybe it looks a little bit like this as well. On the left-hand side, you have procedural fluency. They can do a routine, they can do a routine, they can do a routine. But what if that routine looks slightly different the way it was presented at the start, like I said about variation? What if the question wasn't presented in exactly the same way, that they'd been practiced different fluency over and over? If they understood the concept of what it meant, well, there's that sweet spot in the middle again. But then again, if you only focus on the concept, then what about the practicing of how to do it? So there is the understanding of learning how and learning when and learning how to. It's really important. That sweet spot, again, is slap bang in the middle. Now, Jane Jones, former maths lead for Ofsted, reminds us through the Mathematics Made to Measure paper, emphasise the importance of developing conceptual understanding, by the way, those are words found in the national curriculum, and not just procedural proficiency on its own, giving all pupils the chance to solve problems and reason about their work. Now, some people go down the route of doing a fluency, reasoning and problem solving lesson, and all the pupils try the fluency. Some might move on to the reasoning, and even a smaller number might move into the problem solving. Now, in primary schools, they tend to start with the problem straight away, and the pupils discuss the problem and approach it straight away. But for some reason, secondary schools teach maths in a slightly different way, which is somewhat bizarre. However, it does say there, give all pupils a chance to reason. So that whole class instruction, the whole class discussion is actually incredibly important. And there they are, the three aims of the national curriculum. This is why some people do go down the route of fluency, reasoning and problem solving, the three assessment objectives. But you notice some of the key words that we're noticing here. Conceptual understanding is there. And it also mentions this word varied in the fluency, including through varied and frequent practice. So that variation is coming out in what we expect our pupils to do. So what is mastery? Mastery means that learning is sufficiently embedded, deep, connected, and fluent in order for it to be sustained, built upon, and connected to. In other words, isn't it annoying when you get to year 10 and you're teaching year 7 content again? Was it taught to any depth? Or was it just taught that the kids did it? Oh yeah, they got the answers right. Did they understand it? Drury has a quote on this. Drury's book, How to Teach for Mastery for Maths. A mathematical concept or skill has been mastered when through exploration, clarification, practice and application over time, a person can represent it in multiple ways, has the mathematical language to be able to communicate related ideas, reasoning, discussion in the classroom. Representation in multiple ways, by the way, one of the 5 big ideas from the NCTM, and can think mathematically, reasoning and problem solving, with the concepts that they can independently apply it to a totally new problem in an unfamiliar situation, problem solving, assessment objective 3. So some of the principles underpinning mastery, and these come from a document you can see in your bottom right-hand corner of your screen there. Teach less, but teach it better. Don't try and cram too much in a lesson. I watch a teacher teach adding, subtracting, dividing, and multiplying fractions in one lesson. Nothing was learned. Absolutely nothing was learned. Go slow to go fast, one small step at a time. And there it is, the Rosenshine quote. In a study of mathematics instruction, for instance, the most effective mathematics teacher spent about 23 minutes of a 40-minute period in lecture, demonstration, questioning, and working examples. In contrast, the least effective teacher spent only 11 minutes presenting new material. Go deep to build firm foundations. Depth is simplicity, not complexity, to make it accessible for all. Whole class teaching to maximize the teacher input with additional pre-teaching intervention for those who need it. Now, differentiation for some is a dirty word, but having those high expectations for everybody, and that everybody can achieve these. But it looks like we're talking here. What scaffolds are we going to put in place to ensure that those pupils who have previously struggled don't struggle in this lesson? I didn't say low ability, by the way, because you never know what the pupils might just surprise you with on that lesson on that day. So I've referenced these 5 big ideas a number of times today, and here they are. The bottom left, you can see variation, and we looked a little bit at the concept of variation with a conceptual variation of with our pentagon earlier on. We talked a little bit about coherence and small steps that are easier to take, and representation, which I'll refer to in the next 30-35 minutes or so as well. Mathematical thinking, the top right there, chains of reasoning, the second objective of the national curriculum. And in the bottom right, fluency, the first objective of the national curriculum. And I really think we're in a beautiful stage for maths education at the moment, because Ofsted's EIF, mathematical education research, the NCTM, the national curriculum, all seem to be coming from the same direction at the moment. No one's disagreeing of what good maths teaching is. And again, it's the 25th of May, and today's paper from Ofsted seems to back all this up again. In fact, it quotes these 5 big ideas and talks about the impact of these 5 big ideas as well. And as such, in this presentation, we'll look at how these big ideas are sourced from great worldwide practice and research, examples of how they can be implemented, how they align with the EEF, yes, the Key Stage 2-3 documents as well, improving maths in Key Stage 2 and 3. Once again, reinforcing the fact that maths teaching should not be much different, really, in Key Stage 3 to Key Stage 2. In fact, I don't know why it should be different, except the topics. And then, oh yes, in line with Ofsted's EIF as well, we'll look at that and how these align with the GCSE assessment objectives. I'm hoping we've kind of started doing that already. So I'm going to ask you just to press pause on the video in just a few moments and just to read these questions and give you a chance to think about, well, so far, what do you know? What have you heard so far that makes you think, is there anything we could be doing? So I'll give you a chance just to pause the video. Welcome back. I was talking about variation earlier on and saying about the conceptual understanding of what a pentagon is and what it's also, but also what it's not. But there's also something called intelligent practice when it comes to variation and how we choose our exercises. Look at these questions here. Again, I'd encourage you to press pause and just look at the difference between the two sets of questions. If you've done so, you may have just noticed that actually those sets of questions are exactly the same as each other, but they've been ordered to make you think about what's going on. It's on the left-hand side for set A. In fact, you know what? I've got a camera ready for this one. On the left-hand side for set A, these are just practice. Practice the question, practice the question, practice the question, practice the question. And whatever method is you've been taught to do subtraction, well, you'd notice that you'd just be practicing it. Fine. Okay, practice is important, isn't it? But could we do intelligent practice? Because let's have a look at this one. This number here is called the minuend. This one here, the subtrahend, the language that is being used in primary schools. Just a quick question. Have you ever heard this in secondary schools? In your secondary schools? Just a thought. The minuend here, the subtrahend, the difference is 30. But what have we noticed is that minuend has gone up by 2, has been increased by 2, and so has the subtrahend. So what does that mean for the difference? The difference is the same. Now that in itself is a fascinating concept. It's not just, I'm going to practice taking away this digit. So in fact, let's do this. And what would it be? 120 take away 90. 0 from 0 is 0. 9 from 2, you can't do it. Yes, you can actually. It goes to negatives, but never mind. So I'm going to borrow this 1. Borrow? Are you going to give it back? Or are you going to exchange it from 100 to 10 tens? 12 take away 9 equals 3. The answer is 30. Oh, the next question, 122 take away 92. 2 take away 2 is 0. Do you see the lost opportunity? They're about to find out, get the same answer, but not have noticed and looked at the question and thought, oh, that's interesting. The minuend increased by 2, the subtrahend decreased by 2. And actually, that could be, let's get rid of it, get some space to do some drawing. That could have been done with some lovely representation. So if you're looking at a number line, let's just say that number here is 90. Let's say that number here is 120. My writing is appalling. This difference, as we look on a number line, is 30. Now, if I just shift everything along 2 to the right, the difference is still the same. And pupils can see that and think, the impact of adding 2 to my minuend and my subtrahend made no difference to the difference. This thing here. Oh, I took 3 away from the minuend and 3 away from the subtrahend. The difference is still the same. Now, what they're beginning to understand is the concept of subtraction, what is happening whilst you're performing this task, as opposed to just blindly following this task and they're actually not thinking what it means. There's no understanding of what's going on. It's just doing a task as opposed to, oh, okay, that's interesting. This is the beauty of what we call intelligent practice. And so at this stage, I'm going to go to the new review series released today, which completely had to change my presentation just at the last minute. A review of research into factors that influence the quality of mathematics education. And on this first slide here, it talks about variation in the quality of maths education in England is likely to be the result of the absence of systems and systems thinking. These are the last words in this report, by the way. So likely to be the result of absence of systems and systems thinking. I think that's really powerful for leaders. Now, yes, possible gaps in content, instruction, rehearsal, assessment. Absolutely, that's be going inside. But are you creating the best environment for maths education to flourish? Are you creating the best environment in your school for maths teachers to improve, discuss, and embrace what it is they're teaching? And when we're learning new practice as well. All these slides, by the way, I've just taken little, all these screen grabs are all from the new research released from Ofsted today. Use of intelligent variation in sets of exercises. There's a difference between content that pupils have recently learned and content that develops further in their mind through practice. Both can be planned for. Variation within sets of activities can help, of exercises can help people to learn the ranges and boundaries of strategy applicability. That means, is it the best way? So in fact, you know what, I'll show you an example of that one. I love my camera. I'll show you. If I was doing, let's say, 362 divided by 1, do I really need to go to something called the bus stop, which is not a bus stop, by the way, it's called short division. Oops, I got the number wrong. 362, my apologies. Do I really need to go through this method here? Do I really need to go, how many 1s going to 3? How many 1s going to 6? How many 1s going to 2? So if I go like this, that means I don't understand what is actually going on. What does this sentence here mean? How many ones go into 362? Divided by itself, how many one? Oh, not divided by itself, that's the exact opposite. But divided by 1, that's fascinating that pupils would be doing this. So let's go back to this here, the ranges and boundaries of strategy applicability. This example here would be a sledgehammer used to crack a nut. Important patterns and rules. Connections between varying problems. That's interesting as well. Leaders need to make sure they curate and control this approach. Evidence in collections of tasks given to pupils in China, Hong Kong, and Taiwan. Variation versus variety. Variety is pick and mix. Now, most practice exercises contain variety. Variation has a careful choice of what to vary, as we saw between the minuend and the subtrahend here. Careful choice of what the variation will attempt to draw attention to. This here, variety or variation. I'd call it a variety. There's nothing being achieved by doing these, except, by the way, there's a place for this, and it certainly comes to revision, because you then got to think of lots of different ideas what might happen. But that isn't when we're trying to share ideas for the first time, if you like. This would not be an ideal exercise when we're talking about small steps. This one here, variation, procedural. So I've got procedural variation. So just notice, if I've answered the first question, a third of £12, could I use that to find 2/3 of £12? This isn't just practicing the procedure. I could put any random numbers on the fraction. I could put any random numbers of the amount. But by making there be some kind of relationship between them, the pupils are going to work on the subject and work on the exercise. So if I found 2/3 of £12, can I find 2/3 of £12? And again, I'm going to go to my camera because it's time to introduce one of the other 5 big ideas. So what's the question? 2/3 of £12. Now, if I found 2/3 of £12, my whole is 12. And I'm dividing it into 3 equal parts, because that's what this symbol here means. The denominator of my fraction is saying I've got 3 equal parts, and I'm going to be finding out 2 of them. Now, if I know that I've got 3 parts that total 12, how much does each part equal? Now, this goes back to what they're learning in primary schools about part, whole. 1 plus 1 plus 1, no, that doesn't equal 12. 2 plus 2 plus 2, no, that doesn't equal 12. But actually, there are 3 equal parts of 4, and 4 plus 4 plus 4 equals 12. And this is how pupils are learning addition and subtraction and multiplication, I suppose, and division in primary school. Are we doing enough of this in the secondary school? Because let's see, I wanted 2/3 of £12. So I want 2 of those 3. There we go, 2/3. So the answer equals 8. Now, this becomes quite interesting, because what did on the exercise I showed a moment ago, I said, well, if I know this, can I use that information to find out 2/3 of £24? Well, I'm looking for mathematical connections, and I noticed that 12 is half of 24. I'm doubling 12 to get to 24. So if I double this number, my reason, I conjecture, and I'd be right to do so, that all of these double. So what's 2/3 of 24? The same concept of what I'm trying to achieve here. 2/3 of an amount still exists. This is horrendous, isn't it? I apologize that I've left this in. But 8 plus 8 is 16. But they're seeing the concept of what 2/3 means, as opposed to this just being a couple of numbers, one above the other. And by the way, has anyone ever noticed that this looks a lot like the division symbol? 2 divided by 3. How often do people make that connection, that 2/3 is exactly the same as 2 divided by 3? Not exactly the same, but certainly related. There's lost opportunities sometimes where we just throw random activities at pupils. Variation's got real power. And the central idea of teaching with variation is to highlight the essential features of the concept through varying the non-essential features. It's posited on the view that when certain aspects of a phenomenon vary, like the amount, for example, that we were trying to find fractions of, while other aspects are constant, those aspects that vary are discerned, they're worked out. You're seeing what's going on, getting an understanding of the structure. And that is what we talk about when it comes to representation and structure, one of the 5 big ideas. So I mentioned representation, and here's a question that was taken from Edexcel 2018, and I'll show you the scores that the pupils get first, matter of fact. It looks interesting. It looks maybe somewhat difficult to some. The average score across the country was 1.02 out of 2, and the average score for part 3 was under 1 out of 3. Now I'm going to start to have a go at this question on the camera for you, and I'm going to use representation. And the reason I'm going to do that is because the most successful countries across the world, certainly Singapore, have introduced something called bar modeling. And the idea of representation, not only like it did a moment ago for the fractions of amounts, it exposed the structure of what was going on. But also bar modeling can be used as a tool to solve a problem. So what have we got? Alan, so let me just make a note myself. Alan gets an eighth, Bisbar gets a half, Chan gets the rest, and Alan got £2.50. Okay. I've got to work out how much Bisbar gets, and I'm going to work out the ratio of A to C, Alan to Chan. So then, I'm told that Alan gets an eighth of it, and I'll just make sure this camera works. There we go. If Alan gets an eighth of it, the whole amount, so I need to break it into 8 equal parts. Now, I could have used a computer and done this beforehand, but there's something to be said by showing the pupils me making this so they can do it themselves. Now, I'm told Alan got that. That's fine. Now, is it Bisbar? Got half of them. Now, half of them would be this number here. Okay. Which means Chan gets the rest. I can deduce that. That's fine. That's worth seeing. And I can actually see that's 3 parts out of 8. Now, I was told Alan got £2.50. Okay, so if one part is worth £2.50, I can see that part's worth £2.50, that part's worth £2.50, that part's worth £2.50, that part. You can see where I'm coming from here. Now, I've forgotten what the question was. It was how much was Alan got or how much Bisbar? But whichever one, it doesn't actually matter, because I can see Bisbar got 4 lots of £2.50, which is a tenner. I can see Chan got 3 lots of £2.50, which is £7.50. I can't remember which question it was, but the answer was really simple. Yet, across the country, the average mark was 1.02 out of 2. Now, for the second question, which was out of 3, it said, what was the ratio of Alan to Chan? Well, hold on a second. 1 to 3. I can see that so clearly. The answer was 1 to 3. And that was worth 3 marks on a GCSE. Let's just go back to the question. How much Bisbar gets, that's it. Find the ratio amount of money Alan gets to the amount of money Chan gets. Give your answer in the form A and B where they're whole numbers. And look at the average score. What representation allowed me to see it so quickly. I was able to make deductions. I knew how many Alan was worth £2.50, and so therefore I could see how quickly Bisbar had got £10 because he got 4 equal parts. And how quickly, if I just go back to the camera again, I quickly knew that Chan must have the rest, so I can see Chan has 3 parts. And because each part is £2.50, and what I'm doing here is using derived facts. If I know, then I know something else, and they're incredibly powerful when we're working with pupils. Representation, one of the 5 big ideas, and there it is in the top left-hand corner. Lots of research behind this to say how powerful it can be. The Cockcroft report in 1982 proposing the use of manipulatives in maths lessons. Singapore took that on. The British government didn't because it changed from Labour to Conservative at the time. But the Singaporean government said, right, we need to improve maths teaching. So they took that Cockcroft report. They looked at research by Brunner proposing concrete pictorial abstract. And the EEF now have actually turned around in the last couple of years and said, yes, it's recommendation 3, I think, for Key Stage 2 and 3. I've got my booklet somewhere and I always like to have it near me. In fact, every maths leader should have it near them. And I think it's up there. It is option 2, use maths and representations. One of the biggest levers, if you like, that exposes the structure of the maths and eventually enables pupils to do the maths without the pictures. That's the aim. It's not supposed to be a replacement method. It's supposed to help you understand what's going on. And that is sometimes how maths teachers misunderstand the use of the bar model. They think it's a method. Well, no. What it is a scaffold to the understanding. We still want pupils to be able to understand what's going on. It's not to replace anything. But how often do our teachers talk about that? Further research behind it, bar modeling became Singapore's most popular way of exposing maths pictorially, enabling pupils to solve problems. Now, in this instance I've just done for you, I'm hoping that showed how quickly I was able to solve the problem because I was able to visualize it. The approach has been shown to increase conceptual understanding, AO1 on the national curriculum, we saw it earlier on, and has a positive effect on attainment in English classrooms. So it exposes the structure, it can pull out the concept being taught and the key difficulty point. Now, some representations, I've shown you a number line today. I've done a bar model just very quickly there. Some key representations be met over and over again, which is why they can be so powerful. The fact we can go back to them over and over and over again. And of course, that bottom line then, in the end, students need to be able to do maths without the representation. Let's just see one more example of it and we'll move on. Laura had £240. She spent 5/8 of it. How much money did she have left? Now I've represented it here. Now this would be the first part of the lesson. I don't care about the answer. The answer is just the beginning. And that is an ethos I really believe in. Most people think maths is getting the answer, getting the answer, getting the answer. No, it's not. It's the reasoning of understanding how we got there. That's what's most important. And firstly, can you see what I've done is represent the problem here, and I have not attempted to find the answer. I saw it was 5/8, so I've got 8 equal parts. The whole was 240. What I want to find out is where I put a question mark. This is helping kids with problem solving, not focusing on the answer, but focusing on what we know and therefore what can we derive. And because there are 8 equal parts and they sum to 240, that means each equal part must be 30. 240 divided by 8. And then I can see 3 boxes, which are worth 30 each, must total 90. And suddenly the facts are derived. They make sense. And I can see the concept behind them. And it's not, oh, hold on a second, which method is it I use? Is this the AA squared plus B squared equals C squared rule? Because there are too many rules in maths to learn. Now, why did I choose this example? This came from a paper where it showed that Singaporeans got 78% of them got it right. In America, 25%. And they'd learned how to use a particular representation which enabled pupils to access the structure of the maths and gave them a tool to enable them to succeed. One of the 5 big ideas, representation and structure. So it's time to take a pause now and to reflect somewhat. If representation and variation are 2 of the most effective strategies a maths teacher could introduce, given its use in Key Stage 1 and 2, as I've been talking about, how are you going to encourage its development in Key Stage 3 and beyond? Something for you to consider as leaders, not only in maths department, but across the school as well. So let's move on. Got to say it, got to mention Ofsted. You might like them, you might not. But at the moment, what they're saying is definitely in alignment with what the NCTM are presenting and all sorts of cognitive science. Everything seems to be nicely aligned right now. Now, I mentioned Ofsted have released a new document today, being the 25th of May. So let's just go to that slide and have a look at it. Methods for working algebraically. In algebra, pupils benefit from fewer but powerful representations and an iterative approach to sequencing the facts and procedures for working algebraically. The bar modeling method here can be used as a bridge from arithmetic to early algebra. It's a useful interim method for abstracting arithmetic and algebraic expressions from word problems. In other words, it's helping pupils understand what they're doing. And again, as we mentioned with regards to this document here from the EEF, it's what we're seeing in Key Stage 1 and Key Stage 2. These manipulatives and representations are just tools, and how they're used is essential. Just by throwing the representations out there, that doesn't mean it's suddenly going to work. We've got to learn as teachers how to use them best. However, the Ofsted document from the Education Inspection Framework and how to apply it to the teaching of maths is a very, very useful document. And I like to work with leaders and go through them with this and say, okay, let's tick off each of these. What do you do for this one? How do you know about this one? Are you confident in your own department in this one? And it's a very, very useful document. Teaching models new procedures and uses resources and approaches that enable pupils to understand, not do, understand the maths they are learning. So we've talked about the 5 big ideas, representation, how it gives the conceptual understanding of it and can show the structure of it. Variation helps us get that concept as well. Just talked a little bit about the EEF document that does that, and there it is within the recommendations. These are the recommendations that should be being applied. These are the most current research. Do your department use this? Are they aware of them? By the way, there's a very good RAG rating system for this. You can download it from the EF website and it goes through RAG rating each of those, and you can use that as a grid for department improvement. Pupils understand and remember the mathematical knowledge. Understand and remember. Remember's hard enough. The mathematical knowledge, concepts and procedures appropriate for their starting points, including knowledge of efficient algorithms. Not just any algorithm, but what's the most efficient algorithm for a certain circumstance? Remember that divide by 1 thing I looked at earlier on? Do we really need the bus stop? Ugh, bus stop. So concepts and procedures appropriate. We talked about that earlier on. That sweet spot in the middle. Then yes, we've got to do some practice. Got to be intelligent practice, the procedure. But we need to have that conceptual understanding. Again, AO1 for the GCSE. Appropriate for their starting points. Ensure that prerequisites are challenged and met before teaching begins. That's part of the mastery models we saw earlier on. You don't just start teaching something. Well, do we have the prerequisites, being a hierarchical subject, to build upon it? The the next lesson, unit of work, year or key stage? Absolutely. Does the scheme of work talk about this coherent journey that builds on previous knowledge? Or does it just tell teachers, today you are teaching them simultaneous equations? Okay, well, what about the novice teachers? Do they know what to do? Do they know what they're building on? Are they being given any help? And when I say the word novice teachers, I'm going to be using the word novice teachers shortly when it comes to the new Ofsted release today. Are we talking about not very good teachers as well, who aren't very efficient at the moment? Novice doesn't, the problem with novice makes you think, oh, they've only been teaching a short time. What about the teachers who haven't been teaching effectively for quite a while? The curriculum divides new material into manageable steps, lesson by lesson. So if the teacher's told, right, this week you're doing simultaneous equations, well, what about them? How am I going to introduce it? What will be the first step? What will be the second step? What will be the third step? Novice teachers and non-specialists, there's enough of them out there at the moment. Does the curriculum help them in that respect? And Rosenshine, as I mentioned earlier on, has that idea of saying, look, our working memory is small. So let's look at new material in small steps and go in depth, not just rush and say, right, let's try and cover all this because the curriculum is pushing us to do so. And a new report last year, Low Attainment in Maths, talks about the derived facts and the fact we should be building upon each step one by one. And of course, there it is through the middle there, coherence. The small steps are easier to take, one of the 5 big ideas from the NCTM. So let's introduce coherence. Small steps are easier to take. Focusing on one key point each lesson allows for deep and sustainable learning. I think that's probably the most important things to say there, but it is worth saying this. When introducing new ideas, it's important to make connections with earlier ones. Again, we looked at what we know about cognitive science when we saw those circles and those ovals earlier on. And when something's deeply understood and mastered, it should be used in the next steps of learning. So were you taught a trick that can't be used later on? Because if it's only good, oh, good, there was a trick that got them through today's lesson. Fantastic, they got it right. But then if it doesn't hold up in future lessons, in future mathematics, then you haven't actually helped that pupil's journey whatsoever. And again, we've looked at it there. Teaching in small steps requires time, but again, it was pointed out. Spent more time presenting new material and guiding student practice than did the least effective teachers. This is something that's called the S plan, even though it's not really an S, it's kind of backwards. This could be a journey that teachers consider when they're planning, hopefully together, hopefully collaboratively. What's the first key learning point? Going for simultaneous equations again. What's the first thing they need to understand? Maybe show it as a standard and non-standard. When we talked about standard and non-standard, I showed you earlier on examples with a pentagon. The standard examples were the two that I conjectured that you'd be writing when I asked you to draw a pentagon. But what about all those other pentagons? They were still pentagons. They're huge long ones, but they were still pentagons. The standard and the non-standard. And what points, what misconceptions might the pupils have at this stage? Then let's look at the next key learning point. How can we present it in one way? How can we present it in another way that's still within the realms of understanding that key learning point? But what are the difficulties afterwards? What are the difficulties there? Where do the pupils struggle with this? And there's plenty of research that says knowing knowledge of misconceptions in advance is useful, and it's very difficult for all teachers to know that. So how does your scheme of work talk about those misconceptions? Do your teachers talk to each other about those misconceptions? Do they challenge those misconceptions in the lesson before they happen, so the pupil isn't wasting 20, 30 minutes, and then they realize at the end, when I see AFL at the end of a lesson, oh, that's when I find out they've made mistakes. Oh, great. 30 minutes after making the mistake. Great, you've been making it for 30 minutes. That's fantastic time to do your AFL. So let's use the example of trigonometry, introducing trigonometry and right-angled triangles. Let's break that down into the small steps. Well, before you use SOHCAHTOA, you need to know what a right-angled triangle is. And any maths teacher watching this will know that they've seen pupils try and use SOHCAHTOA to find a missing angle or a missing side on a non-right-angled triangle, which completely is a waste of time. You'll get 0 because you didn't understand the most important part of the concept. It's got to be a right-angled triangle. And you have to take your time in the lesson to ensure they know what a right-angled triangle is and the fact it only applies to right-angled triangles. And that idea of the concept and the non-concept earlier on with the variation. Here was a pentagon. Here was another pentagon. Here's one you haven't done before. Here was one that is not a pentagon. And why? Reasoning, AO2. Here's a right-angled triangle. Here's another right-angled triangle. This one's not a right-angled triangle. Why? Look at all these small steps you could be doing. Using the calculator, just the calculator skill. Then the inverse sine, inverse cosine, inverse tangent using a calculator. That's a skill to be practiced as well. How to rearrange equations, very important with SOHCAHTOA, in inverted commas. Rearrange equations that contain a trigonometric function. I've seen it plenty of times where pupils divide by sine, as if they think sine is a number. But if they've done these 2 small steps beforehand, they understand that sine is a function that takes an input and gives out an output. All these small steps that you take your time to get there and break it down so the kids learn something hierarchical, they can build onto the previous knowledge. We're not trying to put too much into their working memory in one big go. We're making sure they're really good at each part before we carry on. Let's go back to the Ofsted's EIF guidance. Inspectors will consider what steps the school has taken to ensure pupils understand and remember the mathematical knowledge, concepts and procedures appropriate for their starting points. And we can see here this article again, procedural fluency versus conceptual understanding. This document here from 2001, it's an American document. There's these intertwined ideas of maths teaching, but they mention conceptual understanding and procedural fluency as well. Efficient algorithms. And that gets developed by Fluency, one of the 5 big ideas. And it's also, of course, the first assessment objective of the national curriculum. And there are 2 good ways of doing this. Opportunities to select appropriate strategies and then comparing strategies using worked examples. So let's have a look at some of these. The sledgehammer to crack a nut. I've forgotten I was going to mention it. 1,000 take away 7. So 7 from 0. You can't do it, apparently. So I'm going to borrow. I'm not going to give it back, apparently, from the 10. It just takes too long. It's not efficient. It's not the right method to use in this instance. All you're doing is going straight to that, what did we call it? Let's go back a couple of slides. Procedural fluency by showing them this method, but not having any idea of what the concept is. If it's 7 fewer than 1,000, then that shouldn't be necessary to be using this method of subtraction. Again, 9 from 6, you can't do it. So you borrow the 1 and you put the 1 on top instead. What a completely pointless task. Completely pointless task. Just moving the 1 from there to there. Oh yeah, I can do it now. But so if they're just following the procedure, they haven't noticed that themselves. They haven't been asked to think about the question before they've actually done it. How many 7s go into 56? 7s can't go into 5, so I better carry the 5 over. Exactly the same concept there, the idea of, well, I'll just move the 5 to here. They haven't actually looked at the problem before they started it. They just thought, oh, here's a procedure I've got to do. Let's do it. 97 times by 100. 7 times 0 is 0. Another 0 times 7 is 0. 7 times, lots of zeros there. Pretty pointless. Is that really the most efficient strategy? And then to compare, I mean, it will work. Don't get me wrong, it works. But imagine a teacher who takes 2 ideas and says, I've got this idea on a whiteboard, on my imaginary whiteboard here, and another imaginary whiteboard. And you say, this people did this way, they got it right. This people did this way, they got it right. Which do you think was more efficient and why? Best is a difficult word to use and maybe shouldn't be encouraged necessarily, but best in this instance might be all right. Because there would be times that the long multiplication would be a better method, perhaps. But in this instance, I think knowing that multiplying by 10, the numbers shift along the number line or the along the place value, sorry. And that would be explored a bit further for conversation, but getting teachers to explore what methods you use and compare methods and why. There's plenty of research to suggest that. There is the question from a SATS paper, 326 divided by 1, and pupils using the bus stop. Noticing, would you really want to take away 11,999? Or would it be nicer to take away 12,000 and then add 1? 12,000 would be a lot easier. I could do that in my head. So it's 110,456. And in fact, I then just add 1 because I wasn't taking away 12,000. I was taking 1 fewer away, wasn't I? So the answer is 110,457. That would be a lovely one to compare methods. What about this one? 3/5 divided by 3. This one I'm going to do on paper, as a matter of fact. 3/5 divided by 3. Because here's another opportunity when we talk about representation. 3/5. Okay, so there we go. 3/5 is this. And you can see the concept of 3 equal parts out of 5 divided by 3. Well, hold on. That means that divide by 3 is an interesting thing because I haven't even got a whole here. I mean, this here is worth 1. And you might say, well, I can't fit a 3 into it. But what does that sentence here mean? In this context, I want to divide it into 3 equal parts. In this context, 12 divided by 3, how many 3s go into 12? Okay, different context. Here, how many 3s go into 3/5? Doesn't really work. So I have to think of another way of what this sentence means. And again, just being narrow in your descriptions, if you like, of what division is, how many 3s go into, it then limits what you can do with this task. I want to divide it into 3 equal parts. Okay, so here's 3/5. A circle here. That's not a circle, it's an oval. Terrible manners, terrible maths, Tom manners, terrible. I want to divide it into 3 equal parts. How much is 1 worth? There we go. I'm going to divide it into one of those 3. The answer is 1/3. Now, 3/5 divided by, 3/5 divided by 3, you'll get suddenly say the method is keep, flip, change. So keep the first, flip the second, times a third. 3 times 1 is 3, 5 times 3 is 15. That simplifies to a fifth. Yeah, I've already got that answer because I've thought about what the concept is actually asking me to do, what the question's asking me to do. Not, here's another rule, let's go for it. Keep flip change, hooray! Let's keep going. Oh, I've forgotten I've done this. There it is. There's a whole, there's 3/5, one of the 3 equal parts, a fifth. So fluency demands more of learners than memorization or rote is what people will be going on about. Efficiency, accuracy, and the flexibility. I'm going to move on from, I knew these words were coming up, so I wanted to talk about these. Efficiency, using an appropriate strategy, which I think I've referred to a little bit already for you. Accuracy, yes, we've got to get correct solutions, that's fine, but we all understand that. But adapting strategy and transferring across context. In other words, what strategy should I use given the context? So look at this example here, taken from the absolutely brilliant book, Making Every Math Lesson Count. Every math department should have a copy of this. Solve 3 lots of x plus 1 equals 15. By the way, I said 3 lots of, and that's the same as multiplication, isn't it? So you can see that Mullen here, the first thing Mullen does is multiply out the brackets. So 3 lots of x, 3x, 3 lots of 1 is 3. Then they take away 3 from both sides, and they're divided by 3. Mamie thought, I could see a more efficient method. I'm going to divide both sides of my equation by 3 to start, because I know 3 lots of is times, and I can divide both sides by 3 to get rid of this 3, this number outside the brackets, the coefficient of the brackets, if you like. So I think x plus 1 equals 5. Then I've just taken away 1. Now, Mamie's solution here is really nice. It's efficient. What a great opportunity for discussion in a classroom. How often does that discussion take place? You could have said a couple of stems, if you like, that teacher could use in the classroom. What's the same between their methods? The answer. Great. What's different? Well, they both did some subtraction from both sides. Okay, and they did it from both sides as well. They both did division, but in different times. Okay. Did they both work? Yes. Which was quicker? And of course, they can see at the moment, oh, Mamie's is quicker. It's like, okay, does that always work? What about if I change that to 16? Would you still like Mamie's method then? And you're like, oh, no, well, 16 doesn't divide by 3. Well, it does, but it doesn't divide evenly. And you're like, okay, so you don't really want to use that method. So what method are you going to use? Comparing worked examples, comparing methods. Do you still think Mamie's method is better? And get them to discuss that opportunity. And Ofsted said this many years ago, when problems are set, teachers do not use them well enough to discuss with pupils alternative methods and alternative approaches, why one is more elegant than another. That's what mathematicians do. They find the more efficient and elegant ways. The final of the 5 big ideas is mathematical thinking. And what's it mean to think mathematically? It means that the middle one, I think, is really key here. Taught ideas that are understood deeply, not just received passively, but worked on by the students. So received passively would be, this is what you do today, ladies and gentlemen. You divide by the bottom, you divide by the top. Let's do it 30 times. You divide by the bottom, divide by the top. How many did you get right? Well done! They haven't thought about the maths. It needs to be thought about why did we divide by the bottom? What's it mean to divide, multiply by the top? Mathematical thinking can involve looking for pattern to find that structure, looking for relationships. They're deriving those ideas to each other, connecting ideas. Maths is this continual interconnected subject, as we saw at the very beginning. Reasoning logically, as we've seen from Rosenshine's 23 minutes out of 40, like we've seen reasoning in the second of the national curriculum big assessment objectives. Explaining, conjecturing, and proving using the proper language also. This is a beautiful, beautiful slide. And it comes from Can Do Maths, which is a Key Stage 2. In fact, they call this the secondary ready presentation, because they've got one concept there. 7 times 8 is 56. And if I know 7 times 8 is 56, I know 56 divided by 8 equals 7. I know 56 equals 7 times 8, as well as 56 equals 8 times 7. I know 8 equals 56 divided by 7. I know 7 is a factor of 56. I know 8 is a factor of 56. And by the way, all of this is taught in primary school. So why is it most secondary schools I go to, I see them teaching this straight away? Now, is it because they've assumed that it wasn't taught? Oh, we can teach you better. Or they just gone in straight into it, said, oh, we need to teach them this. Or they actually tried to build on what was taught in primary schools. Just a thought. This is all taught in primary schools. Now, this here is the perfect example of derived fact. We know one piece of information in the top left there, 56 equals 7 times 8. And from these, the research last year, the low attainment in maths and investigation of Year 9 students, the one I particularly look at the most here is the derived facts thing. Students rarely use derived facts. If I know one thing, then I know something else. They rarely estimate as well. But teachers don't teach these derived facts explicitly. Now, teachers believe that derived facts are obvious for the students, but they're not, and students are unfamiliar with them. And that's making those connections with mathematics and that smiley girl at the start as to why she liked maths. And we go back to this about all these connections, the circles representing units of knowledge, etc. And with mathematical thinking, I've added one more quote on the bottom there. Professor Coe reminds us that learning happens when pupils have to think hard. And so we said earlier on about in one classroom, those pupils who have done the first work quickly, we don't move on to harder work, a different topic. We do the same topic, but make them think harder through problem solving and give them reasoning activities. And again, meeting the aims of the national curriculum there, reasoning, mathematically solving problems. We have got differentiation by depth. And here it is in the national curriculum's descriptions, if you like. The expectation is the expectation is that majority of pupils will move through the programs of study at broadly the same pace. However, decisions about when to progress should always be based on the security of pupils' understanding and their readiness to progress to the next stage. And this is the point. Pupils who grasp concepts rapidly should be challenged through being offered rich and sophisticated problems before any acceleration through new content. Those who are not sufficiently fluent with earlier material should consolidate their understanding, including through additional practice before moving on. Another reminder, not you go and do another topic. We're always stretching you as your high ability learners. Actually, no, we're giving you more sophisticated problems to think hard, so it's more likely to stick. Memory is the residue of thought, Willingham. Now, Ofsted, of course, are now fully behind this, and I will go back to the Ofsted thing they released today as well. But Jane Jones made very clear that the mastery approach is clearly going to make an impact. And the short answer to whether mastery approach is actually supported by them is yes. Again, reiterating the fact that pupils are expected to move through the programs of study at broadly the same pace. Under the previous curriculum, pupils have tended to be very quickly put on a particular track. The top set are the only ones who do higher, the bottom set are the only ones who will do foundation, and they'll stay there. Instead, Ofsted are of the belief that all pupils should achieve, including pupils from disadvantaged backgrounds. A mastery of maths approach is a vehicle for catching pupils up and keeping them caught up. And from another citation from Jane Jones here, differentiation in the past meant pupils doing different maths. Teachers on a regular basis still produce anything up to 5 different worksheets per lesson. Teachers can't do that. It's not fair on them. Jane and her colleagues would like to see more practical equipment being used. Representation, one of the big 5 big ideas, and their continued use into Key Stage 2, 3, and 4 where appropriate. From this tweet here, Jane Jones responding to Bruno Reddy, will inspectors appreciate schoolwork may appear not to be differentiated? But again, we discussed that national curriculum expectation that pupils will progress at broadly the same speed. The differentiation might need to be more subtle, different depth, AO 1, 2, 3, different approaches, scaffolds to support, different support challenge, the questioning we use, the 23-minute discussion out of 40 minutes. Worth mentioning, Craig Barton's podcast with Jane Jones really goes into a lot of detail there. So I think we've looked at the 5 big ideas in quite a bit of detail today, and I'm hoping you've found those useful over the course of the last hour or so. So let's just quickly remind ourselves of something we've referred to, but I think it's worth pointing out again. Professional learning for all teachers of maths. All those teaching mathematics should have the opportunity to be involved in lifelong professional learning, always honing and deepening elements of knowledge about maths and knowledge about teaching maths. Very different things. I don't consider myself a mathematician in many ways, actually. I think my strongest area is pedagogy, making sure that being a good mathematician is not enough to teach mathematics. Knowledge about maths, knowledge about teaching maths, and there it is on the right hand side. Teachers should continue to develop and evaluate their knowledge, looking at effective ways of explaining, representing and exemplifying math, knowing how to use particular resources. There's no such thing as a good resource. There truly isn't if teachers don't know how to use them properly, if they haven't discussed with other staff how to use them effectively. So that's where I come to the Teaching for Mastery, the journey, the opportunity to develop the maths teachers in your school. In fact, you know what? I should go back to the Ofsted review that came out today because it does say here, high quality maths education may have the following features. School-wide approaches to providing time and resources for teachers to develop subject knowledge and to learn valuable ways of teaching from each other. If I go to another one, leaders can also plan to develop teachers' subject and subject pedagogic knowledge through giving teachers opportunities to work with them and learn from each other. For example, helping new teachers, novice teachers, not high-performing teachers. What's the one I'm looking for as well? Non-specialists. Give them the opportunity to see and adopt useful ways of explaining core concepts, methods, and strategies to the pupils they teach. It would be a shame in a department of 8, let's say 8 sets in a year 7. There is the potential for all of them to be teaching a topic in a completely different way. And when I talk about coherence, imagine that journey through school, that you were shown one made by your year 7 teacher. Then you go to year 8 and you've got a different teacher. And don't be, and I get those schools that turn around to me and say, oh yeah, but we keep our staff the same way all the way through. Do you? Does that teacher stay with them for 5 years, or does some of them leave halfway through? And so suddenly they are going to change to a different teacher. And wondering, in those 8 classes, are they all getting the same diet? Because someone's doing it better. And if someone's doing it better, then the other kids are being disadvantaged. Why are they not sharing the best strategies and the best methods and having some consistency together? So something I'm obviously quite passionate about is the teaching for mastery of the journey. And in the primary school, it looks like the readiness groups, and you get the developing, embedding mastery, sustaining mastery, and there are other hub work groups as well. In the secondary, it starts with the developing, where a specialist will come to your school and support you. What is a work group? Well, the work groups meet several times over the course of a year. It might be usually they do have participants from different schools all come together with a work group lead. One of the things that I do, and the work group aims are linked to teacher professional learning, teacher practice development, and of course are all about improving student learning and improving maths teaching across a whole school or department. Really, really important that if a member does go off to a work group lead, there is something created by the staff back in the school to enable them to share what they've learned so everyone can benefit. Know nothing about the Maths Hubs? Well, there are 40 of them around the country, and I encourage you to go to mathshub.org.uk and go to find out the mailing list of what's being offered. This is the time of year, this is being recorded in May, this is the time of year that the Maths Hubs are putting out programs out there saying, look, these are what are being offered next year, sign up now for the next academic year. And if you want to be one of those schools that is starting your teaching for mastery journey, there are 2 ways of going about it. Let's have a look at that. One of them, then we talk about what's happened last year. This year, we worked with 8 secondary schools on developing the teaching for mastery. This is in the central region. 2 teachers from each school became mastery advocates. And I, as one of the specialists, had 2 schools. So I worked with the 4 teachers. And so I was the specialist who helped them understand the principles. I made them watch the videos on my website before they'd come to me, a bit of a flip learning, so we could go a little bit further in depth in the time I had with them. Then they take that back into their own classrooms, some of the stuff I shared with them, then with teachers within their own department over time to embed these principles and practices with the support of the specialist. The advocates are released. So as a school leader, we'd ask you to release these advocates to join me and other specialists for 6 half-day meetings, development activities in the year. It might end up being a bit more than that in future years' time. They engage in certain tasks. So I would give them some tasks in between to try and support their ongoing professional development. And we really ask schools leadership to be fully supportive of this, either be the head of the department, whoever it might be, whichever work group teacher's taking part, to make sure that they're being given the time to do that, to think about it in their own practice, and also to share it with the department. And I should point out that schools are paid for this. You don't pay for it. You are paid to attend these training. Application forms are now available. It says available later this term. It is now available, certainly for Central, and I'm sure in other Maths Hubs regions as well. At this stage, I know this has been recorded in May, so I'll remind you that the Maths Hubs actually have a second online conference. There are 2 of them taking place this year. They have a bit further on the teaching for mastery, although there are further videos on those on my website. And a summary of the teaching for mastery, 5 big ideas. If you look up on my website on tommanners.co.uk, have I actually done a slide on that? Yes, I have. Brilliant. So there's me when I didn't have a beard and I had shorter hair. If you go to this section here, CPD videos, maths pedagogy videos, and the NCTM's 5 big ideas. In the first section on maths pedagogy videos, there is a video called Teaching for Mastery. How about Teaching for Understanding, which covers in a bit more depth some of the 5 ideas. And then there's a video on each of them as well. There's no money to be made from me doing this website. This is just there for people to enjoy and hopefully to embrace and hopefully to support teachers. So I hope you've enjoyed the last hour or so. I think I've gone over. But as I said, that was all about mastery. I'm worried about pupils understanding it. Maybe I'm more passionate actually about ensuring that teachers get the chance to develop their knowledge and the chances, the opportunity to be considering over and over, can they be better so their pupils can do better? If you've got any complaints, thoughts, queries, make the complaints brief, but feel free to get in touch with me through Twitter or on my email address there, mail@tommanners.co.uk. Thank you very much for listening. I hope you enjoyed it. And again, if you do have any questions, please do ask. But the biggest tip, sign up for your Maths Hub. It's the reason I'm as passionate as I am is because of what I've been doing through the Maths Hub. I've thoroughly enjoyed it, and I hope your school can start that journey as well.